Here's a number, 9,461,000,000,000 kilometers. Go ahead, read it again. Let it sit there for a second. Now, what does that number actually mean to you? Honestly, not the textbook definition, not the Wikipedia summary you half read in high school. I mean, what does it feel like? What image does it conjure in your mind when you try to hold that number, to actually grasp it, to press your fingers around it and understand what it represents in physical, real, tangible space? Nothing, right? Don't worry. That's not a failure of imagination on your part. That's a failure of the number itself to connect with the part of your brain that understands distance. Your brain evolved over millions of years to navigate spaces that range from about 1 centimeter to about 1,000 kilometers. Below a centimeter, things get blurry and abstract. Above 1,000 kilometers, say the distance from London to Rome, most people start losing their grip on what it actually means. The number 9,461,000,000,000,000 doesn't just exceed what your brain can picture. It exceeds it by a factor of roughly 10 billion. Your brain isn't equipped for this the same way a ruler isn't equipped to measure the distance to the moon. It's not a failure of the ruler, it's just the wrong tool. That's not your fault. That number is so large it basically breaks the part of your brain designed to understand distance. Our minds evolved to navigate the African savanna, to judge whether a predator was 30 meters away or 300. We were never built for 9 trillion kilometers. No human being was. And yet that number, 9,461,000,000,000 kilometers, is just 1 light year. 1. A single unit of cosmic distance so routine in astronomy that scientists use it the way you use the word mile, casually, in passing, without blinking. 1. A single unit of cosmic distance so routine in astronomy that scientists use it the way you use the word mile, casually, in passing, without blinking. The Andromeda Galaxy is 2.537 million light-years away. The edge of the observable universe is 46.5 billion light-years from Earth. The nearest star to our sun is 4.24 light-years. We hear these figures and we nod. We feel vaguely impressed. And then we move on with our lives because our brains have quietly filed the numbers under big and called it a day, which is actually insane if you think about it. Because there is something out there, a real place, a real destination, an actual expanse of physical reality. And we've essentially agreed as a civilization to just not understand how far away it is. But here's what's wild. Here's the thing that made me want to make this video. In the last few years, and especially with the data coming back from the James Webb Space Telescope, astronomers haven't just been measuring these distances. They've been redefining how we think about them. New parallax measurements, gravitational lensing recalibrations, Cepheid variable star recalibrations. The universe, it turns out, might be slightly larger than we thought, or structured differently, or expanding faster. And every single one of those revelations comes back to the same foundational question that, embarrassingly, most of us have never truly answered. How far away is a light year? Not numerically, viscerally, cosmically, in a way that actually changes how you look at the night sky. That's what this video is. We are going to build the true scale of the universe from the ground up, one stepping stone at a time, using every analogy, every thought experiment, every jaw-dropping comparison I can find, until the number 9,461,000,000,000,000,000 kilometers doesn't just mean something to you, until it haunts you, because it should. Let's start somewhere familiar. Chapter 1: The Lie We Were All Told. Let me tell you about the moment most people first encountered the concept of a light year. It was probably a classroom, maybe a documentary, maybe a parent pointing up at the night sky and saying, with great authority, "Those stars are light years away. That means the light you're seeing right now left that star thousands of years ago. You're seeing the past." And you thought, cool, wow, the past, amazing, that's kind of poetic. And then you moved on. Nobody stopped to ask the follow-up question. Nobody said, okay, but how far is that actually? Because the phrase light years had already done its job. It had signaled incomprehensible distance, and your brain accepted that signal and settled in. It stopped pushing. It filed it under things that are very, very far and never looked back. This is the lie we were all told. Not a malicious lie, not even a deliberate one, just a quiet, casual abdication of curiosity, a cultural habit of reaching for awe without ever reaching for understanding. And the irony is that understanding light years, truly understanding them, is so much more awe-inspiring than the vague, hand-wavy version we all settled for. So let's undo it. Let's start from scratch. First, the definition, the real one, not the glossed-over version. A light year is not a unit of time. This trips people up constantly, and honestly, it's an understandable confusion. The word year is right there in the name, so brains default to duration. People hear light year and assume it means something like a very long time. Movie characters misuse it constantly. That joke is so last year, we're talking light years behind the times. And that linguistic slippage has quietly infected how most people mentally categorize the term. But a light year is a unit of distance. Specifically, it is the distance that light travels through the vacuum of space in 1 year, moving at its maximum possible speed. It is a distance, a gap, a stretch of empty space with two ends. And to understand how far that gap actually is, you need to start with the speed of light, because the two are inseparable. That speed is approximately 299,792 kilometers per second. Per second. Not per hour. Not per minute. Per second. Right now, as you watch this video, light is crossing nearly 300,000 kilometers every single second. In 1 second, light could circle the entire Earth 7.5 times. In 1 second. While you blinked, light lapped the planet 7 times. To put that another way, the Earth is about 40,000 kilometers around at the equator. Light crosses that distance in 0.13 seconds. You cannot blink faster than light can circumnavigate the Earth. Your eyelid hasn't even started to move before light has already lapped the planet and is starting its second lap. Let's do one more comparison before we move on, because I want this speed to land. The International Space Station orbits Earth at roughly 7.7 kilometers per second. Astronauts on the ISS experience 16 sunrises every single day because they're moving so fast that they lap the entire planet every 90 minutes. It is the fastest sustained human habitation in history. Light is 38,900 times faster than the ISS. In the time it takes the ISS to travel 1 kilometer, light has already crossed the entire diameter of the Earth. So take that speed, that ungodly, physics-defying, nothing can touch its speed, and let it run for a year. Let it go for 365 days, 24 hours a day, 7 days a week, never stopping, never slowing, never resting, just blazing through empty space at 299,792 kilometers every single second. At the end of that year, you've covered 9,461 billion kilometers, about 5.88 trillion miles. That's 1 light year. Now, here's where it gets interesting, because knowing the number still isn't enough. We need a framework. We need something to hang it on, some reference point from the world of human experience, or the number just floats there, enormous and meaningless, like so many cosmic figures do. So let me give you the first of several anchors. The fastest object ever built by human hands is the Parker Solar Probe. Launched in 2018 by NASA, it dives toward the Sun in a series of ever-tightening orbits. And at its closest approach, it reaches speeds of around 690,000 kilometers per hour. That is, without exaggeration, almost incomprehensibly fast by any human standard. It's the fastest thing we've ever made. It would get from New York to London in about 20 seconds. If you drove a car at highway speed from New York to London, ignoring the ocean, it would take roughly 74 hours. The Parker Solar Probe does it while you reach for your drink. Now, how long would the Parker Solar Probe take to travel 1 light year? About 6,500 years. Let that settle. Our fastest spacecraft, the most breathtaking feat of engineering in human history, would need 6,500 years just to cover 1 light year. 1. To put that in perspective, 6,500 years ago, the ancient Egyptians hadn't yet built the pyramids. Writing had barely been invented. Civilization itself was only just getting started. If we had launched the Parker Solar Probe on the day the first human city was founded, it would only just be arriving at the 1 light year mark today. And it still wouldn't have reached the nearest star. Here's another way to feel that. Imagine every human being who has ever lived. Estimates vary, but demographers think roughly 108 billion humans have been born since our species emerged. If each of those 108 billion people lived an average of 40 years, their combined lifespans would add up to about 4.3 trillion person-years. The Parker Solar Probe, flying for 6,500 years, covers 1 light year in less time than the total accumulated lifespans of every human who has ever drawn breath. We haven't been alive long enough as a species to send a probe 1 light year, not even close. The nearest star to our sun, Proxima Centauri, is 4.24 light years away. At Parker Solar Probe speed, about 27,500 years. Let's keep going because this exercise is important. The Milky Way galaxy, the spinning disk of stars and gas and dust that we call home, is roughly 100,000 light years across. If we sent the Parker Solar Probe straight across the galaxy at full speed, it would take approximately 650 million years to reach the other side. For context, 650 million years ago, the most complex life on Earth was soft-bodied ocean creatures. The dinosaurs hadn't evolved yet. Mammals hadn't evolved yet. Flowers hadn't evolved yet. Trees hadn't evolved yet. The continents didn't look anything like they do today. And our spacecraft would still be less than 1% of the way across the galaxy. This is the moment, right here, where most science communication stops. It shows you the big numbers, lets you feel appropriately humbled, and wraps up with something like, the universe is unimaginably vast. And sure, yes, it is. But we're not stopping here, because the reason the universe is this vast, the reason light years are this enormous, traces directly back to the one physical law that underlies all of this, the one cosmic speed limit that shapes the entire structure of reality as we know it. The speed of light is not just a convenient measuring stick. It is the most fundamental constraint in the universe. And to understand why light years feel so impossible to cross, you need to understand why nothing can go faster than light. Not just that it can't. Why? Chapter 2, The Speed of Light, the universe's only speed limit. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that quietly rearranged the entire architecture of reality. His name was Albert Einstein. You've heard of him? The paper was called On the Electrodynamics of Moving Bodies, and it introduced the world to the special theory of relativity. And at the heart of that theory was a proposition so strange, so counterintuitive, so aggressively at odds with everyday experience, that physicists initially resisted it with everything they had. The proposition was this: the speed of light in a vacuum is constant, not constant relative to the Earth, not constant relative to the Sun, constant relative to everything. No matter how fast you're moving, no matter in which direction, no matter what your reference frame. If you measure the speed of light, you will always get the same number, 299,792 kilometers per second. This sounds reasonable until you think about it carefully. Imagine you're standing by the side of a road. A car drives past you at 60 kilometers per hour. Inside that car, someone throws a ball forward at 20 kilometers per hour. From your perspective by the roadside, how fast is the ball moving? 80 kilometers per hour. The speeds add together. This is Galilean relativity, the thing your brain instinctively does when combining velocities. It's intuitive. It's how the physical world works for every normal object you've ever interacted with. Now apply the same logic to light. Imagine a spaceship traveling toward you at half the speed of light. The crew of that spaceship turns on a torch and shines it in your direction. How fast does that light arrive at you? Your brain says 1.5 times the speed of light. Half from the ship plus the full speed of light from the torch. Simple addition, right? Wrong. The light arrives at exactly the speed of light. Not 1.5 times, not 1.0001 times. Exactly, precisely, to every decimal place that has ever been measured, across every experiment that has ever been run. 299,792 kilometers per second. This is not a rounding error. This is not a limitation of our instruments. This is not something that more advanced technology will eventually correct. This is a fundamental, bedrock feature of the universe, and it breaks our intuition completely. Einstein realized that if the speed of light is constant for all observers, then time and space themselves cannot be constant. They have to be flexible. They have to stretch and compress in order to make the speed of light come out the same for everyone. This is where we get time dilation. The faster you move, the slower time passes for you relative to a stationary observer. And length contraction. The faster you move, the shorter you become in the direction of travel from the perspective of that stationary observer. Space and time are not fixed backdrops against which the universe plays out. They are dynamic, malleable, interconnected dimensions. Einstein called the combination space-time, and the structure of space-time is what creates the light year as a natural unit. Because light, alone among all things, always travels through space-time at the same rate. This isn't just abstract mathematics. We've measured time dilation directly. GPS satellites orbit the Earth at about 14,000 kilometers per hour. That's fast enough that time runs slightly slower for them than for clocks on the ground, by about 7 microseconds per day due to their velocity. Simultaneously, because they're farther from Earth's gravitational field, general relativity means time runs slightly faster for them, by about 45 microseconds per day. The net effect is that GPS satellite clocks gain about 38 microseconds per day relative to ground clocks. 38 microseconds sounds trivial, but GPS systems rely on timing signals accurate to nanoseconds. If we didn't correct for relativistic time dilation every single day, GPS would accumulate errors of roughly 10 kilometers per day. Your navigation app would be useless within weeks. Every time you use GPS to navigate, you are relying on Einstein's relativity being correct. The universe's speed limit is not a philosophical curiosity. It has practical consequences we depend on daily. But here's the part that locks in the cosmic speed limit, and I want you to really feel this. As you accelerate any object with mass, any object at all, from a particle to a spacecraft to a planet, it gets harder and harder to push. Specifically, the object's effective inertia increases as its speed increases. The faster it goes, the more energy you need to push it even faster. At 10% of the speed of light, this effect is small. At 50%, it's noticeable. At 90%, it's enormous. At 99% of the speed of light, the object's effective inertia has ballooned to about 7 times its rest mass. At 99.9%, about 22 times. At 99.99%, about 70 times. The math is unambiguous and brutal. To push a massive object all the way to the speed of light, you would need an infinite amount of energy. Infinite. Not a lot. Not more than we can currently generate. Infinite. There is no amount of fuel, no size of engine, no technological advancement that gets around this. The laws of physics themselves close the door, bolt it, and then brick up the wall. Only massless particles, photons, the particles of light, can travel at light speed. Because they have no mass to resist the acceleration, they're already going as fast as anything can go the moment they're created. They have never not been going the speed of light. So why does this matter for light years? Because it means that the distance represented by a light year, the distance light covers in a year, is not just very far. It is the maximum possible rate at which information, matter, or energy can propagate through space. 1 light year is 1 year's worth of the absolute cosmic speed limit. It is the furthest that any signal, any effect, any influence can possibly reach in 12 months. When you look at the night sky and see Proxima Centauri, the light entering your eyes left that star 4.24 years ago. That's not a quaint astronomical fact. That's the universe telling you. This is how long it takes to cross that gulf, even going as fast as anything in existence can possibly go. There is no shortcut. There is no workaround. The gap is what it is. But wait, there's actually a subtlety here that most people miss, and it makes the story stranger and more beautiful. Remember time dilation? The fact that a moving clock runs slow? Here's what that means for a hypothetical interstellar traveler. Imagine we somehow built a spacecraft that could accelerate continuously at 1 g, the same gravitational pull you feel standing on Earth right now, which is roughly 9.8 meters per second squared. At that rate of acceleration, the crew would feel perfectly comfortable, as if they were standing in a normal room, and the ship would keep getting faster and faster. At 1 g of continuous acceleration, you'd reach the speed of light in about 1 year of ship time. Except you can't actually reach light speed. So what actually happens is you approach it asymptotically, getting closer and closer, but never quite there, while time on the ship begins to dilate dramatically relative to Earth. Here's the extraordinary result of the mathematics. At 1 g continuous acceleration, you could cross the entire Milky Way, 100,000 light years, in about 12 years of crew time. Not 100,000 years, 12 years. Because as you get closer and closer to the speed of light, time on the ship compresses so dramatically that vast distances pass in what feels like a short time to the crew. But when the ship turned around and came back to Earth, it would find that 200,000 years had passed. The Milky Way of 200,000 years from now. Every person the crew had ever known would be dead, and so would the civilization, the language, the culture, the planet's surface as they'd known it. The crew would return as strangers to a future so remote it might as well be science fiction. This is time dilation taken to its logical extreme. You could theoretically traverse the universe in a human lifetime, but the universe you returned to would be unimaginably old. The speed of light isn't just a barrier to reaching other stars. It's a one-way door in time. This is why we say light years are impossible to cross. Not because the physics forbids the journey in principle, but because the physics makes the journey a death sentence for everything you've left behind. Now here's where this gets even more unsettling, and this is the part that a lot of popular science glosses over. Einstein's equations don't just constrain how fast things move through space. They also connect to something called the Hubble expansion. The fact that the universe itself is expanding, that the fabric of space-time is stretching in all directions simultaneously. And here is the critical, mind-bending distinction. Space-time itself is not subject to the speed of light limit. The expansion of the universe can and does carry distant objects away from us faster than light. Not because anything is moving through space faster than light, but because the space between objects is growing. It's like drawing dots on a balloon and then inflating it. The dots aren't moving, but the distance between them grows. This is why the observable universe has a radius of about 46.5 billion light-years, even though the universe is only about 13.8 billion years old. The light from the farthest objects we can see left them 13.8 billion years ago. But in the time that light was traveling to us, the universe expanded so much that those objects are now 46.5 billion light years away. We'll get to that later. We'll get to what it means to peer at the actual edge of the observable universe and what lies beyond it. But first, let's come back to Earth, literally. Because before we lose ourselves in the enormous, we need to build the scale from the bottom up. And the bottom starts right here, in our own solar system, the patch of space that most people think of as home, and which is already, on closer inspection, almost incomprehensibly large. Chapter 3, Our Own Backyard. Here's a question most people get wrong. How long does it take sunlight to reach Earth? If you said instantly, you've been lied to by everyday experience. If you said 8 minutes, you're exactly right, and you probably already know more about this than average. 8 minutes and 20 seconds, give or take. That's the travel time for a photon fired from the surface of the sun to reach your face here on Earth. The sun is approximately 150 million kilometers away, a distance astronomers call 1 astronomical unit, or AU, and light covers that gap in just over 8 minutes. Think about what that means. Right now, the sunlight warming the back of your hand departed the sun before your last cup of coffee finished brewing, before your last short meeting started. If the sun suddenly, inexplicably, vanished from existence this very second, you wouldn't know for 8 minutes and 20 seconds. You'd sit there, going about your life, eating your lunch, scrolling your phone, completely unaware that your star was gone, until suddenly the light disappeared and the sky went black. 8 minutes of blissful ignorance. The cosmic delay is built into the universe at the hardware level. This is the first place where the speed of light shifts from being an abstract physics fact into something viscerally eerie. But 8 minutes is still fast, in the grand scheme. We're still in the neighborhood. Let's walk the neighborhood properly, because most people have never actually done this. Built up the solar system scale from scratch, in light travel time. The moon is about 384,000 kilometers from Earth. Light covers that in about 1.28 seconds. When you look at the full moon on a clear night, you're seeing it as it was 1.28 seconds ago. In the context of light years, that's nothing. In the context of human space travel, though, it took the Apollo astronauts 3 days to get there. 3 days. For a distance, that light crosses in slightly over 1 second. The fastest we've ever sent humans anywhere took 259,200 seconds, and the light does it in 1.28. Mars, our nearest planetary neighbor, depending on where both planets are in their respective orbits, sits somewhere between 3 and 22 light minutes away. When the Perseverance rover is trundling across Jezero crater and sends a signal back to Earth, that signal travels at the speed of light, and it still takes up to 22 minutes to arrive. Mission controllers can't send a real-time command and get an instantaneous response. Every instruction they issue has a built-in delay of up to 22 minutes before the rover even receives it, let alone before they see its reaction. The speed of light is not a theoretical constraint for future space travel. It is a practical engineering challenge right now, today, for missions already operating in our own solar system. Jupiter, about 43 to 52 light minutes away. Saturn, between 70 and 90 light minutes. Uranus, between 2.5 and 3 light hours. Neptune, roughly 4 light hours at its closest. Pluto, at the far edge of what most people think of as the solar system, is on average about 5.5 light hours from Earth. The New Horizons spacecraft, which launched in January 2006 and flew past Pluto in July 2015, took 9.5 years to get there. 9.5 years of continuous travel at a launch speed of roughly 58,000 kilometers per hour for a destination 5.5 light hours away. You could travel that same distance at the speed of light and cover it before your morning is over. But here's the thing about Pluto that most people don't know. It is not even close to the edge of the solar system. The Kuiper Belt, the ring of icy bodies, dwarf planets, and rocky debris that Pluto is part of, extends out to about 50 astronomical units from the Sun, roughly 7 light hours. Beyond that is the scattered disk, a sparser region of icy objects on highly elliptical orbits. And beyond that, at the truly outermost edge of the Sun's gravitational reach, is the Oort cloud. The Oort cloud is a vast, roughly spherical shell of comets and icy bodies that surrounds the entire inner solar system like a soap bubble around a grain of rice. It was first proposed by the Dutch astronomer Jan Oort in 1950, based on the orbits of long-period comets that seemed to come from all directions, which implied a roughly spherical source region very far from the Sun. We've never directly observed the Oort cloud, but we can infer its existence from the comets that occasionally fall inward toward the Sun when they're disturbed, perhaps by a passing star or the gravitational ripples of the galaxy itself. When a comet like Hale-Bopp blazes across the sky every few thousand years, it's a visitor from the Oort cloud, a chunk of ice and rock that has spent billions of years in the deep freeze of the outer solar system, dislodged by some distant gravitational nudge, falling inward on an enormous elliptical orbit to briefly warm itself in the Sun's light before disappearing back into the dark for another millennium. Those dramatic, once-in-a-generation comets are postcards from the edge of our solar system, from distances measured in fractions of a light year. How far does the Oort cloud extend? Best current estimates put its outer boundary at somewhere between 50,000 and 100,000 astronomical units from the Sun. That is approximately 1 to 1.5 light years, 1 to 1.5 light years just to reach the outermost boundary of our own solar system. The solar system, our solar system, the Sun's system, the gravitational territory of our star, stretches almost halfway to the nearest other star. Voyager 1, launched in 1977, is the farthest human-made object from Earth. As of right now, it's about 23 billion kilometers away, roughly 21.5 light hours out. It has been traveling for nearly 50 years, 50 years of continuous flight, launched on a trajectory designed to exploit gravitational assists from Jupiter and Saturn to fling it outward faster than any rocket alone could manage. 50 years. Think about what has happened on Earth in 50 years. The internet was invented. Humans mapped the human genome. The Berlin Wall fell. The Soviet Union collapsed. Smartphones went from science fiction to universal. 50 years of civilizational change, and Voyager 1 has covered 21.5 light hours. and it hasn't even reached the inner Oort cloud yet. At its current speed, Voyager 1 will take approximately 300 years to reach the inner edge of the Oort cloud, and somewhere between 14,000 and 28,000 years to exit the Oort cloud entirely and enter the true interstellar medium, the vast, cold, nearly empty space between stars. This is the solar system, the patch of space we live in, the address on the cosmic envelope, and it's already staggering, already almost unnavigable at any speed available to us. But in cosmic terms, in the language of light years, it is a dust mote, a footnote. The nearest star is 4.24 light years away. After those 28,000 years, after Voyager 1 finally clears the Oort cloud, having been in flight for longer than all of recorded human history, it will still have more than 4 light years to go before it reaches anything. 4 light years of empty, silent, pitch-black vacuum. That gap between stars is what we're going to next. Chapter 4, The Nearest Stars, a Census of the Void. Let's talk about Proxima Centauri. It is the closest star to our Sun. It sits 4.24 light years from Earth. And in 2016, astronomers announced something remarkable. It has a planet. A rocky, Earth-sized world orbiting in what's called the habitable zone, the orbital band around a star where liquid water could theoretically pool on a planet's surface. They called it Proxima Centauri b, and in 2020, a second potential planet was announced, and then a third candidate in 2022. The discovery genuinely electrified the scientific community. Here was a potentially habitable world, possibly several, sitting at our nearest stellar neighbor. In cosmic terms, it's practically next door. But here's what practically next door actually means in cold, hard numbers. If we launched the Parker Solar Probe, our fastest ever spacecraft, on a direct trajectory to Proxima Centauri b, it would arrive in approximately 27,500 years. If we sent Voyager 1, which is already drifting in roughly the right direction, it would take about 73,000 years to get there. 73,000 years ago, Homo sapiens had barely left Africa. Language might not yet have reached its modern complexity. No art, no agriculture, no cities, no writing, no science. None of it had happened yet. And the spacecraft would still be traveling. Even proposed future technologies, the kind that exist on research papers and whiteboards, paint a sobering picture. Breakthrough Starshot, an initiative backed partly by the late Stephen Hawking, proposed sending tiny laser-propelled light sail probes to Proxima Centauri at roughly 20% of the speed of light. At that speed, the journey would take approximately 20 years. 20 years is vastly more manageable than 73,000. But those probes would be the size of a postage stamp. They would carry no crew, no meaningful scientific instruments by current standards, and no ability to slow down when they arrive. They'd simply zip through the Proxima Centauri system and keep going. And even the infrastructure to build and fire such probes is decades away from existence. The point is this: 4.24 light years is not a distance we have any practical mechanism to bridge within a human lifetime. Not now. Arguably not ever, given the physics. Proxima Centauri is not alone in its neighborhood. It's part of a triple star system, the Alpha Centauri system. Alpha Centauri A and Alpha Centauri B are 2 two sun-like stars that orbit each other in a gravitational dance, their center of mass completing one mutual orbit roughly every 80 years. They sit at 4.37 light-years from Earth. Proxima is a much smaller, dimmer red dwarf that loops around this pair from a much greater distance, taking perhaps millions of years to complete one orbit. So within a sphere of about 4.4 light-years, centered on our Sun, 3 stars. Now let's expand the bubble. Within 10 light-years of Earth, how many stars are there? About 10 individual stellar systems. Some are single stars, some are binaries. The total count of individual stars is somewhere around 16, but many are faint red dwarfs, barely bright enough to be called stars at all. 10 star systems in a sphere, 20 light-years across. That's extraordinarily sparse. If you scaled the Sun down to the size of a grain of sand, the nearest grain of sand, the nearest other star, would be several kilometers away. The solar neighborhood, despite what the word neighborhood implies, is mostly empty space, with isolated stars separated from their nearest companions by gulfs that dwarf anything in human experience. Out to 50 light-years, we have roughly 1,400 star systems. Many of those are now being found to have planets, multiple planets in many cases. But 50 light-years is already an almost unbridgeable chasm. A radio signal from Earth, which also travels at the speed of light because radio waves are a form of electromagnetic radiation, sent toward a star 50 light-years away right now, would arrive there in 50 years. Any response would take another 50 years. A conversation with any potential civilization at 50 light-years would take a century per round trip. Your great-grandchild would receive the reply to a question you asked today. This is the structural loneliness of interstellar space. Not poetic loneliness, physical, mathematical, electromagnetic loneliness. The universe makes it structurally very hard for anything, signals, ships, information, to bridge the gaps between stars. And yet, strangely, there's something almost comforting in it. Every photon of starlight that reaches your eyes is a survivor. It has crossed light-years of empty, hostile vacuum, dodging dust grains and magnetic fields, losing brothers and sisters to absorption along the way, and it made it to your retina. When you look at the night sky, you're receiving mail that was sent years, decades, centuries ago. The universe is slow, but it delivers. Let me give you some stars you might recognize by name. Sirius, the brightest star in the night sky, that brilliant blue-white point of light you can see on a clear winter night, the one that seems to flash different colors as it twinkles near the horizon. It's 8.6 light-years from Earth. The photons entering your eyes right now left Sirius in 2015. Epsilon Eridani, one of the closest sun-like stars, long a favorite target of SETI researchers looking for signs of intelligent life. 10.5 light-years away. Tau Ceti, another sun-like star confirmed to have at least 4 planets in its system, one potentially in the habitable zone. 11.9 light-years. Barnard's star, a red dwarf just 6 light-years away, the 4th closest stellar object to Earth, moving across our sky faster than any other star due to its relatively close distance and high proper motion. When your great-great-grandchildren look up at the night sky a few thousand years from now, Barnard's star will have visibly shifted position relative to the background stars. A slow crawl across the constellations, that our own brief lifetimes are too short to notice. And here's something worth sitting with for a moment. All of these stars, Proxima, Sirius, Epsilon Eridani, Tau Ceti, Barnard's star, have been visible to human eyes since the first humans looked up at the sky. Our ancestors named the constellations they belonged to, built myths around them, navigated by them, worshipped them. And during every one of those thousands of years of human stargazing, not a single person who looked at those lights had any idea how far away they were. They were just bright points on a dark canvas. It wasn't until the 1830s, less than 200 years ago, that the first successful measurement of stellar parallax gave us our first genuine calculation of stellar distance. Friedrich Bessel measured the parallax of a star called 61 Cygni in 1838 and determined it was about 10.4 light-years away. For the first time in human history, we had put a number on the void between stars. The number was stunning, and we've been grappling with its implications ever since. All of these stars are, in the professional vocabulary of astronomers, our immediate local neighborhood. And not a single one of them is reachable in any human lifetime with any technology that currently exists or is credibly on the near horizon. Now let's pull back further, not just to 50 light years, not to 100, but to the scale of the whole Milky Way, where things stop being distances between individual stars and start to being distances between the vast structures those stars form. Because out to 1,000 light years, we encompass tens of thousands of stars. And that entire 1,000 light year bubble is still only 2% of the distance from us to the galactic center. We haven't even left the suburbs of our own galaxy, which means it's time, finally, to talk about the Milky Way itself, to zoom out far enough to see the whole thing, and to feel what 100,000 light years of galaxy actually contains. Chapter 5: The Milky Way, 100,000 light years of home. On a clear, dark night, far from city lights, somewhere truly rural, you can see it. A faint, milky band of light arching across the entire sky from horizon to horizon. Soft and diffuse, like someone dragged a wet brush across a dark canvas. It doesn't look like much at first glance. But if you let your eyes adjust, if you really look, it deepens. You start to see variations in brightness, dark lanes cutting through the glow, denser clumps and sparser regions. It's not uniform, it's structured. It's a galaxy, and you're inside it, looking along its disk from the inside out. For most of human history, nobody knew what it was. The ancient Greeks thought it was a spill of milk from the goddess Hera's breast, which is literally how it got its name. The Milky Way, the Milky Road. Galaxy from the Greek word galaxias, meaning milky. What it actually is, somewhere between 200 and 400 billion stars. 200 to 400 billion stars, all gravitationally bound into a single, rotating disk approximately 100,000 light years across, roughly 1,000 light years thick at the disk, with a central bulge, perhaps 10,000 light years thick, swelling up at the hub. The entire structure, stars, nebulae, stellar nurseries, black holes, gas clouds, dust lanes, ancient globular clusters, is embedded in a halo of dark matter that may extend several 100,000 light years in every direction, like an invisible scaffolding that the visible galaxy hangs inside. And when you look at that milky stripe across the night sky, You're looking at the disk of that structure edge on. You're inside it. You're one of those 400 billion stars worth of solar systems, one dot among hundreds of billions, gazing outward along the flat plane of your own galaxy, watching the combined light of billions of stars, too remote to individually distinguish, blur into that soft, ghostly band. It is one of the most extraordinary things you can do with your naked eyes. Find a dark field, lie on your back, look up. That is 400 billion suns. Now let's really try, to feel the scale of it. We said the Milky Way is 100,000 light years across. Let me translate that into kilometers just to have the full number on the table. It's approximately 946 trillion kilometers, close to a quintillion kilometers. That number is utterly, completely, irreparably meaningless to the human brain. So let's go back to the only method that actually works: ratios, anchors, and comparisons. Parker Solar Probe, our fastest spacecraft, 690,000 kilometers per hour. Time to cross the Milky Way at that speed, approximately 650 million years. When 650 million years ago was, there were no land animals, no insects, no plants on land at all. The oceans contained mostly soft-bodied creatures and early shellfish. The entire subsequent history of complex life on land, the age of fish, the age of amphibians, the age of reptiles, the age of dinosaurs, the age of mammals, the age of humans, would all unfold in the time it takes our fastest spacecraft to cross the galaxy. Voyager 1, traveling at roughly 61,000 kilometers per hour, has been flying for nearly 50 years. To cross the Milky Way at Voyager 1 speed, approximately 4 billion years. The age of the Earth. And at the speed of light, the physically impossible maximum, achievable only by massless particles, you still need 100,000 years. The entire span from early modern humans through the ice ages, through the invention of agriculture, through the birth of every civilization in history, through every war and empire and renaissance and industrial revolution and digital age, and light, going at maximum speed, would have just barely crossed the galaxy. 100,000 years of human history doesn't even cross one galaxy at the fastest speed the laws of physics allow. Let me tell you what the Milky Way actually looks like in structure, because the scale isn't just spatial, it's architectural. The Milky Way is a barred spiral galaxy. From a vantage point, millions of light years above the galactic plane, it would look something like a cosmic pinwheel. A bright, dense central hub, cut through by a bar of stars stretching maybe 27,000 light years end to end, with 4 major spiral arms: the Perseus arm, the Scutum Centaurus arm, the Sagittarius arm, and the outer arm, sweeping outward from the ends of the bar like smoke trails from a spinning firework. Between these major arms are smaller partial arms and spurs. Our solar system sits on one of these, the Orion spur, sometimes called the Orion arm, nestled between the Perseus arm and the Sagittarius arm, about 26,000 light years from the galactic center. At the very center of the Milky Way, deep behind curtains of dust and gas that block visible light completely, there is a supermassive black hole called Sagittarius A star. Its mass, approximately 4 million times the mass of our Sun. 4 million solar masses compressed into a singularity, wrapped in an event horizon with a diameter of about 24 million kilometers, roughly 17 times the diameter of the Sun itself. In 2022, the Event Horizon Telescope collaboration, a network of radio telescopes spread across the entire Earth, captured the first ever image of Sagittarius, a star, a glowing asymmetric ring of superheated gas with a dark center, an eerie orange halo around a shadow, exactly matching the predictions of Einstein's general relativity. The image was published to front pages around the world. But here's the part that hit me hardest when I thought about it. That image was captured using light that left the region around Sagittarius A star approximately 26,000 years ago. When those photons began their journey, the world's oldest cave paintings had only just been made. Woolly mammoths still roamed the Earth. The last ice age was at its maximum extent. And those photons had been traveling at the speed of light across 26,000 light-years of galaxy for the entire span of human prehistory until they hit the dishes of our radio telescopes and formed that orange ring on our screens. We photographed a black hole with ancient light older than civilization itself. The Milky Way is rotating. The disk spins around the galactic center like a slow cosmic clock. Our solar system completes one full orbit around Sagittarius, a star roughly every 225 to 250 million years. Astronomers call this interval a galactic year or cosmic year. In the 4.6 billion year history of our solar system, we've completed somewhere between 18 and 20 of these galactic orbits. We've been around the galactic block 18 times. Here's a timeline that should rewire how you think about deep time. One galactic year ago, the Triassic period was just beginning. The first dinosaurs were only just evolving. The supercontinent Pangaea was starting to split apart. 2 galactic years ago, the Permian mass extinction had just wiped out 96% of all marine species, the worst extinction event in Earth's history. 4 galactic years ago, the first multicellular life was beginning to appear. 18 galactic years ago, the solar system itself didn't yet exist. We orbit a 4 million solar mass black hole, 26,000 light-years from the center, taking 250 million years per lap, at a velocity of about 828,000 kilometers per hour. This is not a metaphor. This is not poetry. This is happening right now, while you watch this video, while you sit in your chair, feeling entirely still. You are not still. You are spinning on a planet that is orbiting a star that is hurtling around a galaxy at 828,000 kilometers per hour. And that galaxy contains up to 400 billion stars. Here's the number that for me hits hardest of all, harder than any of the distances. If you tried to count the stars in the Milky Way at a rate of 1 per second, no sleeping, no breaks, 1 star per second continuously, it would take over 12,000 years, longer than all of recorded human civilization, from the first Sumerian city-states to right now, just to count them, and you still wouldn't have finished. Many of those stars have planets. The data from NASA's Kepler Space Telescope and TESS mission has allowed astronomers to extrapolate that the Milky Way likely contains at least 1 planet per star on average, meaning somewhere between 100 billion and 400 billion planets exist in our galaxy alone. Conservative estimates suggest at least 11 billion of those might be roughly Earth-sized and orbiting within their star's habitable zone. 11 billion potentially habitable worlds. in one galaxy. Think about what that means alongside the distances we've been discussing. Every single one of those 11 billion worlds is separated from Earth by at minimum a few light years, and most by thousands or tens of thousands. Even if the nearest one harbored a civilization right now, a civilization with radio telescopes pointing them at us, broadcasting their existence, we might not hear them for thousands of years. And if we sent them a response, they might receive it in a civilization so different from the one that sent it as to be unrecognizable. The Milky Way may be teeming with life, and we might never know. Not because the life isn't there, but because the distances are so enormous that the signals take longer to cross than civilizations tend to last. 100,000 light years of home, and we can't even shout across it. But now is when we step outside. Now is when we pull back far enough to see the Milky Way from the outside, to look at it not as home, but as a single object in a larger scene. Imagine pulling back from the surface of the Earth until the whole planet is visible, then pulling back until the solar system is a small dot, then pulling back until the Milky Way's entire 100,000 light-year disk, all 400 billion stars, all those billions of planets, all that unfathomable distance we've just spent so long exploring, shrinks to the size of a dinner plate in your field of view. And then you look around, and you see that there are other dinner plates, lots of them. The Milky Way is not alone, not even close to alone. It has neighbors, it has a neighborhood. It belongs to a cluster of galaxies, which belongs to a supercluster of galaxy groups, which sits in a cosmic web of filaments and voids stretching hundreds of millions of light years in every direction. And the distances between those galaxies make the distances within the Milky Way look small, not just larger, not just comparable, small. Everything we've covered, the 8-minute sunlight, the 4.24 light-year gap to Proxima, the 27,500-year Parker probe journey, the 100,000 light-year span of the galaxy, all of it becomes just a single rung on a staircase that goes so much further up than any of us are naturally prepared to comprehend. We're going there next. Chapter 6. The local group. When galaxies are the new unit, let's take a moment to reset. Here's where we are. We started at Earth. We worked our way out through the solar system, 8 light minutes to the Sun, 4 light hours to Neptune, 1 to 2 light years to the edge of the Oort cloud. We zoomed out to the stellar neighborhood, 4.24 light years to Proxima Centauri, a sparsely populated void of individual stars, separated by chasms that would take our fastest spacecraft tens of thousands of years to cross. And then we pulled back to the Milky Way, 100,000 light years of spiral, disk, 200 to 400 billion stars, our galactic home, so large that light itself needs 100,000 years to cross it. And at every step, the previous scale shrank to nothing. The solar system, which took us a full chapter to cross, became invisible within the stellar neighborhood. The stellar neighborhood became a dust speck within the Milky Way. And now, as we step outside the Milky Way for the first time, the entire Milky Way, 100,000 light years of everything we've ever known, is about to do the same thing. It's about to shrink. The Milky Way has neighbors. The two most prominent are called the Large Magellanic Cloud and the Small Magellanic Cloud. satellite galaxies that orbit the Milky Way the way the moon orbits the Earth. On dark, clear nights in the southern hemisphere, you can see them with the naked eye. Two faint, detached patches of sky, like small clouds that didn't get the memo about staying below the horizon. The Large Magellanic Cloud is approximately 160,000 light-years from Earth. The Small Magellanic Cloud sits at about 200,000 light-years. Take a breath here. Those two galaxies, each containing hundreds of millions of stars, each a significant cosmic structure in their own right, are our closest galactic neighbors. And they are 1.5 to 2 times the diameter of the Milky Way away, which means if you were somehow standing on the farthest edge of our galaxy, looking outward toward the Magellanic Clouds, you'd still have more distance to cover than the entire Milky Way is wide. This is the first time we've had to reach for a unit bigger than the Milky Way, and we're only at the nearest neighbors. Now, the Milky Way and its satellites are not isolated. They belong to a larger gravitationally bound structure called the Local Group, a collection of roughly 80 galaxies that are all tied together by mutual gravity, moving through space as a loose, extended family. The Local Group spans approximately 10 million light-years. 10 million light-years. You remember how the Milky Way, 100,000 light-years wide, incomprehensibly vast, became the unit of comparison for Chapter 5? Now the Milky Way is the new stepping stone. The Local Group is 100 Milky Ways across. 100 full diameters of our home galaxy, end to end, just to map the immediate neighborhood. The 3 biggest members are the Milky Way, the Triangulum Galaxy, also called M33, and the Andromeda Galaxy. And it's the Andromeda Galaxy I want to focus on, because Andromeda is the most important object in the sky that nobody ever really thinks about. Andromeda, catalogued as Messier 31, or M31, is visible with the naked eye on a clear night. It's the most distant object you can see without a telescope, appearing as a faint, elongated smudge near the constellation Cassiopeia. Most people, if they've ever noticed it at all, assume it's a star. It doesn't look like much. It's barely resolved as anything more than a soft haze. What it actually is, the largest galaxy in the Local Group, a spiral galaxy roughly 220,000 light-years across, containing somewhere in the region of 1 trillion stars. It is, by most measures, bigger than the Milky Way, though the Milky Way may have more mass when dark matter is included. It is 2.537 million light-years away. Let me write that out. 2,537,000 light-years. That is 2,537,000 times 9.46 trillion kilometers. The number has so many zeros, it stops being meaningful as a number entirely. So let's try to feel it differently. That faint smudge you can barely see in the dark sky, the light reaching your eyes right now, the photons entering your pupils this very second, left Andromeda 2.537 million years ago. That was during the Pleistocene epoch. Homo sapiens did not exist yet. Our ancestors were Homo habilis, early humans who had just figured out how to chip stone into rough tools. They had no language as we understand it. No fire, perhaps, or only the beginnings of it. No art, no religion, no society recognizable to us. and the light those early humans might have seen leaving Andromeda is still traveling. It hasn't reached us yet. It won't for another couple of million years. The faint smudge you see in the sky tonight is ancient history you're observing in real time. Now, Andromeda and the Milky Way are not just sitting still. They are on a collision course. Due to mutual gravitational attraction, our galaxy and Andromeda are approaching each other at roughly 110 kilometers per second. In approximately 4.5 billion years, they will collide. Or more precisely, they will pass through each other, because galaxies are mostly empty space, and stellar collisions during galactic mergers are actually rare. But the structure of both galaxies will be utterly transformed. The two spiral disks will be shredded and redistributed into a new, merged elliptical galaxy. Some astronomers have already named the result Milkomeda, or sometimes Milkdromeda. The night sky in 4.5 billion years, assuming any beings are there to see it, will look nothing like ours. Andromeda will dominate the view, a vast, warped disk filling a huge arc of sky, visibly approaching, visibly distorting. And then the merger will begin, and the sky will be full of chaos. New star formation triggered by colliding gas clouds, brilliant blue star clusters blazing briefly before going supernova, the night sky ablaze in ways our current sky can barely hint at. But that's 4.5 billion years away. Right now, Andromeda is 2.537 million light-years away, and it's the closest large galaxy to us, and it spans a region of space 220,000 light-years wide, and it barely registers as a smudge to the naked eye. Outside the three major galaxies, the local group contains dozens of smaller satellite galaxies, dwarf ellipticals, dwarf spheroidals, irregular galaxies. They cluster around the Milky Way and Andromeda like attendants. Some are so faint and diffuse that they were only discovered relatively recently. The Canis Major dwarf galaxy, thought to be the closest satellite to the Milky Way, wasn't identified until 2003. The whole local group, all 80-odd galaxies spanning 10 million light-years, is, in the grand scheme of things, still just a tiny corner of something vastly larger. And that something larger is called the Virgo supercluster. The Virgo supercluster contains the local group, along with at least 100 other galaxy groups and clusters, spread over a region about 110 million light-years across. 110 million light-years. The local group is one small knot in a web that spans more than 1,000 Milky Ways end to end. And even the Virgo supercluster, vast as it is just a tendril on the edge of something even larger. In 2014, a team of astronomers led by R. Brent Tully at the University of Hawaii mapped the gravitational flows of tens of thousands of galaxies, tracing which way things are moving, which gravitational attractors are pulling them, and discovered that the Virgo supercluster is itself a small part of an immense superstructure they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of superclusters. It contains roughly 100,000 galaxies. It spans approximately 520 million light-years. And the entire Virgo supercluster, which already contained the local group, which already contained the Milky Way, which already contained 400 billion stars, is less than 1% of Laniakea's volume. 1%. We've done this trick now several times. Every time we zoom out, everything that came before becomes a rounding error. The neighborhood becomes a dot. The galaxy becomes a smudge. The supercluster becomes a footnote. But here's the thing about Laniakea that I haven't told you yet. The thing that turns it from a number into something you can almost picture. Laniakea is not a blob. It's not a sphere. It's not a cloud of galaxies, evenly distributed through space like raisins in a cake. It's a web. At the very largest scales, the universe has structure. Not random structure, deliberate, almost architectural structure, shaped by the interplay of gravity and dark matter and the initial conditions of the Big Bang. Galaxies are not scattered uniformly. They cluster along vast filaments, enormous cosmic threads, each one hundreds of millions of light years long, made of gas and dark matter and punctuated along their length by clusters of galaxies. These filaments intersect at nodes called galaxy clusters, some of the densest, most massive structures in the universe. And between the filaments, there are voids, vast, nearly empty regions of space, hundreds of millions of light years across, containing almost nothing. This structure, filaments, nodes, voids, is called the cosmic web. And it is one of the most beautiful and strange things science has ever revealed about the universe. Think about it like, hey, this. If you could step back far enough that entire superclusters like Laniakea shrank to the size of dots, the universe would look like a three-dimensional foam, like the lace pattern in a soap bubble, like the neural network of an impossibly enormous brain. Glowing filaments of matter and galaxies, separated by vast dark voids, interconnected at brilliant nodes, stretching in every direction as far as any light or instrument has ever reached. The Sloan Great Wall, one of the largest known structures in the universe, is a filament of galaxies and galaxy clusters, approximately 1.4 billion light-years long. The Hercules Corona Borealis Great Wall, detected in 2013 through gamma-ray burst distributions, may stretch as far as 10 billion light-years. That's more than 10% of the diameter of the entire observable universe, occupied by a single, loosely bound superstructure. A single structure. 10 billion light-years long. 1 light-year is 9.46 trillion kilometers. 10 billion light-years is 9.46 times 10 to the power of 22 kilometers. If you tried to write that number out in full, it would take more digits than this page can hold. And that's not the universe. That's one filament in the universe. The cosmic web is what the universe looks like from the outside, if outside were possible. It is the largest canvas anything has ever been painted on. And Laniakea, our home supercluster, containing 100,000 galaxies, 520 million light-years wide, is one single node in that web. One node. And we haven't even reached the observable universe yet. Chapter 7, The Observable Universe, the Last Horizon. Here is a sentence that should not be as easy to say as it is. The observable universe is approximately 93 billion light-years across. The observable universe. Not the whole universe, just the part we can see. The part that light has had time to reach us from, given the age of the universe and the expansion of space-time. 93 billion light-years. Let's put that in perspective. The Milky Way is 100,000 light-years across. The observable universe is 930,000 Milky Ways from one side to the other. Laniakea. That 520 million light-year superstructure containing 100,000 galaxies fits into the observable universe about 180 times. 180 Laniakeas side by side to cross the observable universe. Now let's talk about what the observable universe actually contains. Because it's not just space, it's full. Astronomers estimate there are approximately 2 trillion galaxies in the observable universe. 2 trillion. 2,000 billion. In 2016, that estimate was revised upward significantly from the previous figure of around 200 billion, based on Hubble Space Telescope data and new modeling techniques. We keep finding more. 2 trillion galaxies, many of which, like the Milky Way, contain hundreds of billions of stars. Some galaxies, like the elliptical giant IC 1101, contain over 100 trillion stars. 100 trillion in one galaxy. If every star in the observable universe were a grain of sand, you would have more grains of sand than all the beaches and deserts on Earth combined, multiplied by a number too large to write meaningfully on this page. And yet, here's the genuinely haunting part. We can only see any of this because light has had time to reach us. The observable universe is not the universe. It's just the part of the universe visible from our specific location, limited by the speed of light and the age of the cosmos. The universe almost certainly extends far beyond what we can observe. How far? We don't know. It could be 10 times the size of the observable universe. It could be 1,000 times. It could be infinite. Current cosmological models allow for all of these possibilities. What we can say is this: the universe has a hard observational horizon, a spherical boundary centered on Earth, beyond which light has not had time to reach us since the Big Bang. And that horizon is not a wall. It's not the edge of space. Space doesn't end there. It's just the limit of our sight. Everything beyond it could be identical to what we see inside. More galaxies, more stars, more planets, more cosmic web, more structure, more potential, more unimaginable distance. And we would have no way of knowing because the light hasn't arrived yet. We are in a bubble. A 46.5 billion light-year radius bubble of knowable reality, swimming in an ocean of space we cannot see and may never see. Now let me tell you about what we've recently learned from the edge of that bubble, because this is where the James Webb Space Telescope enters the story, and where recent discoveries have quietly rewritten parts of our understanding of cosmic distance. The James Webb Space Telescope, launched on Christmas Day 2021 and reaching its operational position at the L2 Lagrange point by January 2022, is the most powerful space telescope ever built. Its primary mirror is 6.5 meters across, made of 18 gold-coated beryllium hexagons. It observes primarily in the infrared, which allows it to see through dust clouds and, critically, to detect light that has been stretched to longer wavelengths by the expansion of the universe. That stretching is called redshift. When a light source is moving away from you, its light waves are compressed in the direction of travel and stretched behind it, like the sound waves of a passing ambulance. In space, because the universe is expanding, every distant galaxy is receding from us, and its light is redshifted proportionally to its distance. The more redshifted a galaxy's light, the farther away it is, and the further back in time we're seeing it. Webb was designed to see further back in time than any telescope before it, to observe galaxies formed within the first few 100 million years after the Big Bang, when the universe was less than 5% of its current age. And in its very first year of operation, it delivered results that stunned the scientific community. In July 2022, the first deep field image from Webb was released. In a patch of sky so small it could be covered by a grain of sand, held at arm's length, there were thousands of galaxies. Not stars, galaxies. Each one containing billions of stars, many of them older and more distant than any previously confirmed observations. And then the numbers started coming in. Webb began identifying galaxies at redshifts higher than anything previously confirmed. Galaxy candidates at redshifts of 12, 13, 16, corresponding to distances of over 30 billion light-years, and time periods as early as 300 to 400 million years after the Big Bang. Some candidates, if confirmed, would represent galaxies observed when the universe was less than 350 million years old, less than 3% of its current age. But the discovery that created the most discussion, the one that really rattled the community, wasn't just about seeing far. It was about what those far galaxies looked like. According to standard cosmological models, galaxies that old shouldn't look like that. The very early universe was expected to contain only young, irregular, chaotic proto-galaxies, messy accumulations of gas and stars, still figuring out what shape to be. But some of what Webb found appeared to be well-developed, structured, massive galaxies. Galaxies that seemed to have assembled their mass faster than models predicted was possible. In other words, galaxies at extreme distances that appeared to be too old, too big, too organized for their age. Some researchers proposed that this might require revisions to cosmological models. Others suggested the observations could be explained by dust, obscuring the true colors and apparent ages. The debate is ongoing. What's not in debate is what it means for our understanding of distance. Webb is pushing the observable horizon in a way that is forcing cosmology to confront its own assumptions. The edge of the observable universe isn't a fixed, comfortable boundary. Every new instrument we build, every improvement in sensitivity shows us more, earlier galaxies, greater distances, a cosmos that keeps revealing new structure at the very limits of our vision. And what we keep finding is the same thing. More structure, more scale, more galaxies, more light that has been traveling for billions of years just to reach the inside of a telescope, floating silently in space. Here's a thought experiment to close this chapter. Pick a direction, any direction. Point your finger at a random patch of the night sky, not at a star, not at a planet, just a blank seeming piece of darkness. What's out there, in that direction, at the very edge of what Webb could theoretically see? A galaxy, or many galaxies, probably a cluster of galaxies, and beyond them, more galaxies. All the way to the edge of the observable universe, 46.5 billion light years in the direction your finger is pointing. In that single line of sight, stretching from here to the horizon of reality, there may be hundreds of thousands of individual galaxies, each containing hundreds of billions of stars, most of those stars circled by planets. In one random direction, off the top of your head, in a patch of sky you just picked blindly. This is the universe we live in, and we're still not done. because there's one more number, one more step outward, and it is genuinely unlike anything that came before it. Chapter 8, the true edge of everything, and what lies beyond it. Let's talk about what it means for the universe to have a beginning. 13.8 billion years ago, as near as we can measure, the universe began, not in the sense that there was emptiness and then matter appeared inside it, in the sense that space-time itself did not exist before that point. Space began. Time began. Everything that would become the galaxies, the stars, the planets, the atoms in your body, it was all there, compressed into a state of unimaginable density and temperature. And then it expanded. The Big Bang. And from that moment, light began to travel. In the first seconds, the universe was so dense and hot that it was opaque. Photons couldn't travel any distance before colliding with something. The universe was essentially fog. Then, about 380,000 years in, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. The fog cleared. Light could travel freely for the first time. The light released at that moment, the photons that streamed outward when the universe first became transparent, is still traveling today. It has been flying through an expanding universe for 13.8 billion years, stretched by cosmic expansion from its original short wavelengths all the way down to microwaves. We call it the cosmic microwave background, or CMB, and it is detectable from every direction in the sky. A faint, almost perfectly uniform hiss of ancient light. That is the farthest thing we can see. The CMB surface, the spherical boundary where that first light was emitted, is the edge of our observable universe, and it is approximately 46.5 billion light-years away. But here's what I want you to hold on to. Here's what makes this the final escalation. The stuff that emitted that light, the matter that was at the CMB surface, when those first photons set off on their 13.8 billion year journey, that matter has not been stationary. The universe has been expanding this entire time, carrying everything in it farther apart. The stuff that emitted the CMB light was, at the moment of emission, much closer to us than 46.5 billion light years. But in the billions of years it took that light to reach us, the expansion of the universe has moved it away. It is now, right now, somewhere around 46 billion light years from here. That stuff, those original hydrogen atoms from 380,000 years after the Big Bang, is still out there. It has been forming galaxies, stars, planets, possibly life, possibly civilizations, for 13.8 billion years. And it is currently 46 billion light years away, moving away from us faster than light. Not because it's moving through space faster than light, but because the expansion of space itself is carrying it away at those speeds. We will never see it again, not because it's gone, but because the universe between us is expanding faster than light can cross it. Any new light emitted from those regions right now will never reach us. The universe is expanding so fast at those distances that the gap grows faster than light can close it. There's a sphere around Earth, called the Hubble sphere, or sometimes the Hubble volume, beyond which nothing will ever be able to reach us again. Everything outside that sphere is being carried away by expansion faster than light speed. Any signal sent from outside, it will never arrive. Any civilization beyond it is, in the most literal sense of the word, permanently and irrevocably beyond contact. Not because of hostility, not because of technology, because of physics. Sit with that for a second, because it's one of the most quietly devastating facts in cosmology, and it almost never gets the attention it deserves. Somewhere out there, right now, there may be civilizations, advanced, curious, possibly ancient civilizations, broadcasting signals in every direction, exactly as we've been doing with our radio and television transmissions since the early 20th century. Some of those civilizations may have been broadcasting for millions of years. And if they're beyond the Hubble sphere, those signals will never reach us. Not because they're too faint, not because we haven't built the right receiver, because the expansion of the universe is carrying the space between us apart faster than the signals can cross it. The signals are moving at the speed of light through space, but the space itself is expanding faster, and the gap widens with every passing second. There are regions of the universe, entire volumes of space that may contain billions of galaxies, that are now cosmologically isolated from us. They were not always. In the early universe, when everything was closer together and the expansion was slower, light could reach between regions that are now permanently separated. But as the universe expands and the expansion accelerates, driven by dark energy, that mysterious force that constitutes about 68% of the total energy content of the universe, more and more of the cosmos slips beyond the horizon. In the very far future, tens of billions of years from now, even the galaxies currently visible to us will have receded beyond the horizon. The local group will remain, held together by its own gravity. But every other galaxy, every other cluster, every other supercluster will have moved beyond the boundary from which we can receive any new light. The night sky will slowly empty. Distant galaxies will redshift into invisibility. And any civilization arising in that far future, looking at the sky from within the Milky Way Andromeda merger, will see a universe that looks almost empty. No visible galaxies beyond their local group. No evidence of the cosmic web. No hint that there are trillions of galaxies beyond the horizon. They might conclude the universe is small, local, just their galaxy and a handful of companions. They would be catastrophically wrong, but they would have no way of knowing. The universe is not just vast right now. It is becoming less knowable with time. We live in a privileged era, one of the few windows in cosmic history when the universe is old enough to have produced stars and planets and beings capable of observing it, but young enough that we can still see deep into the cosmic web, still detect the CMB, still measure the geometry of the observable universe. A few billion years in either direction and the picture would be radically, misleadingly incomplete. We are lucky, cosmically, absurdly lucky, not just to exist, but to exist right now. The observable universe is not just the limit of what we can see. It is increasingly the limit of what we can ever influence or be influenced by. And this is where the numbers do something final and definitive. The observable universe is 93 billion light-years across. Inside that sphere are approximately 2 trillion galaxies. Each of those galaxies contains, on average, perhaps 100 billion stars. The total number of stars in the observable universe is estimated at around 10 to the power of 24, 1 septillion. A septillion stars. 10 times more stars than grains of sand on all of Earth's beaches. And outside the observable universe, more. How much more, we don't know. But measurements of the CMB, particularly its flatness, the fact that the universe appears geometrically flat at the largest scales we can measure, suggest that if the universe has a finite size, it must be vastly larger than the observable portion. Some estimates, based on the flatness measurements from the Planck satellite, suggest the full universe is at minimum 250 times the diameter of the observable portion. At minimum. Other models, particularly inflationary cosmology, which proposes that the universe underwent a period of exponential expansion in its first fraction of a second, suggest the true universe could be vastly, incomprehensibly larger. Some inflationary models allow for a universe trillions of times larger than what we can observe, or effectively infinite. Infinite. That word is so overused in casual conversation that its genuine meaning has been hollowed out. We say infinite patience, infinite possibilities, infinite scroll. None of those are infinite. Infinite means without bound, without edge, without end. If the universe is infinite, truly infinite, then every possible arrangement of matter that doesn't violate the laws of physics exists somewhere in it. Not metaphorically, actually, including copies of Earth, including copies of you reading these words, having made slightly different decisions, including every possible history, including structures so vast they would make the observable universe look like a subatomic particle. We don't know if the universe is infinite. We may never know, because any evidence either way lies beyond the cosmic horizon. But we know it's at least 93 billion light-years across. We know it contains at least 2 trillion galaxies. And we know that every step we've taken in this video, from Earth to the Moon, to the Sun, to the Oort cloud, to Proxima Centauri, to the Milky Way, to the local group, to Laniakea, every single step has involved the previous scale shrinking to a point. The Earth shrinks to a dot next to the Sun. The solar system shrinks to a dot within the stellar neighborhood. The stellar neighborhood shrinks to a dot within the Milky Way. The Milky Way shrinks to a dot within the local group. The local group shrinks to a dot within Laniakea. Laniakea shrinks to a dot within the observable universe. The observable universe is a dot within the full universe, whatever it actually is. And at every level, every dot was made of 9.46 trillion kilometer steps, 1 light year. The distance light travels in 1 year. That's the unit. That's the ruler. And we need hundreds of billions of them, laid end to end, just to measure the bubble we can see. Conclusion: what you're looking at, let me bring you back to Earth, not metaphorically, literally, back to you wherever you are. A city, a suburb, a bedroom, a commute. Back to the planet, which is about 12,700 kilometers across. Back to the human scale. Your kitchen, your street, the drive to work, the distance to a friend's house. Because here's the thing I want to leave you with. Everything we've covered in this video, every number, every analogy, every dizzying escalation of scale, exists out there right now. Not in the past, not in some abstract theoretical space. Right now, as you watch this, the universe is out there at full scale, real, physical, ongoing. The Oort cloud is there, a vast spherical halo of silent comets, 1.5 light-years from the sun you stood under today. Proxima Centauri is there, 4.24 light-years away. a small red star that may have a rocky planet circling it in the habitable zone. The light from that star is hitting Earth right now. It left 4 years ago. The Milky Way's bar is there. The central bulge is there. Sagittarius A star, the 4 million solar mass black hole, 26,000 light years from where you're sitting, it's there. The light you'd need to see it left 26,000 years ago. The Andromeda galaxy is there, 2.537 million light years away, on a slow motion collision course with us, visible tonight as a faint smudge if you know where to look. The 2 trillion galaxies Webb can detect are there, some of them 30+ billion light years away, their light having crossed most of the observable universe to land on a gold-coated mirror floating in space near Earth. All of it is happening. All of it is real. All of it is now. And you, with your 1.7 meter body on a planet 12,700 kilometers across, orbiting a star that is one of 400 billion in a galaxy, that is one of 2 trillion in an observable universe, 93 billion light years wide. You are not separate from that. You are continuous with it. The atoms in your body were forged in stars that exploded billions of years ago. The iron in your blood was made in a dying star that went supernova before our solar system formed. You are made of ancient light, ancient heat, ancient pressure, ancient time. You are the universe looking at itself. And that phrase gets thrown around so often it's almost lost its impact. But I want you to try to feel what it actually means, given everything we've walked through. Out of 2 trillion galaxies, out of more stars than grains of sand on every beach on Earth, out of 13.8 billion years of expansion, cooling, condensing, collapsing, igniting. Out of all of that, matter arranged itself into something that can understand what 9.46 trillion kilometers means. That can look at the faint smudge of Andromeda and know, actually know, not just intuit, but know through centuries of careful observation and mathematics and physics, that the light is 2.537 million years old, that can build a gold mirror telescope, launch it into space on a rocket, and use it to photograph galaxies from 300 million years after the universe began. You are an extraordinarily improbable arrangement of matter, and part of what makes you improbable is that you can ask, how far away is a light year? Not as a homework question, not as a trivia challenge, but as a genuine act of reaching outward, of trying to hold the universe in your mind, even though the universe is vastly, absurdly, almost offensively too large to hold. And here's what I want you to take away from all of this. Not just the numbers, not just the analogies, but the emotional reality of the situation. Those numbers are not abstract. They are not decorative. They are the actual geometry of the place you live. And most of humanity wanders through that place without ever really looking at it, without ever standing at night under a dark sky and thinking, that faint patch of light is 2.537 million light years away, and it contains 1 trillion stars, and it's coming toward us. We live inside one of the most spectacular and incomprehensible structures in the known universe, possibly in the entire universe, and we spend most of our time not noticing. I don't say that as a criticism. I say it as an invitation. But before I send you out with that invitation, I want to tell you one more thing. Something that doesn't get talked about enough in videos like this one. something that I think is actually the most extraordinary part of the whole story. Everything we've measured, every single number in this video, we figured out from here. We didn't go there. We couldn't. We're stuck on a rock orbiting a medium-sized star in the suburbs of an average galaxy. We have sent exactly one spacecraft beyond the heliopause, the edge of the sun's influence, and it has been flying for nearly 50 years and covered less than a light day. We are, in the most literal sense, trapped. And yet, using nothing but light, the same light that reaches you from a candle, from a screen, from the sky, we have measured the distance to the nearest star, to the center of the galaxy, to Andromeda, to galaxies 13 billion light-years away. We have mapped the structure of the cosmic web. We have photographed the shadow of a black hole 26,000 light-years away. We have detected the faint afterglow of the Big Bang itself, a signal from 380,000 years after the universe began. We did all of that without leaving. The techniques are extraordinary. Parallax, the tiny apparent shift in a nearby star's position as Earth moves around its orbit, allowed us to triangulate the distances to the nearest stars with a precision that would make a surveyor weep. Cepheid variable stars, stars that pulsate at a rate directly linked to their intrinsic brightness, gave us a standard candle we could use to measure distances to other galaxies. Type 1, supernovae, exploding stars with a known maximum brightness, extended that ruler further still. Gravitational lensing, the way massive objects bend the path of light from even more distant sources, gave us another tool, and it's a tool that uses the geometry of space-time itself as a measuring instrument. And every time we built a better telescope, a more sensitive detector, a more precise calibration technique, the numbers shifted slightly. The Hubble constant, the rate at which the universe is expanding, is still being debated because different measurement techniques give slightly different answers, and that tension, that disagreement between methods, is one of the most active frontiers in modern cosmology. It's called the Hubble tension, and it may point toward physics we don't yet understand. New particles, new forces, modifications to our model of dark energy. The universe, in other words, is not fully measured. It is still being understood. The numbers in this video are our best current answers, not final ones. That's not a caveat. That's an invitation of a different kind. The story isn't over. The measurements are still being refined. The James Webb Space Telescope is still sending data. The Vera Rubin Observatory is about to come online and survey the southern sky in unprecedented detail. The next generation of extremely large ground-based telescopes, the ELT, the GMT, the TMT, will push the resolution of our observations further still. The distances will get sharper. The early universe will get clearer, and there will, almost certainly, be surprises. There always are, because the universe does not care about our models. It does not adjust itself to fit our theories. Every time we've assumed we understood it, every time we thought the picture was basically complete, it has revealed a new layer of structure, a new scale of complexity, a new distance to grapple with. Dark matter, dark energy, the accelerating expansion, the Hubble tension, early galaxies that are too big, too organized, too old for our models. Every one of these is the universe saying, "You're close, but you're not there yet. Keep looking, keep measuring, keep asking the question. How far away is a light year? We're still finding out. Go outside on a clear night. Find a dark spot if you can. Let your eyes adjust for 10 or 15 minutes. Look at the Milky Way, that soft, diffuse smear across the sky. And remember, that's not a painting. That's the combined light of hundreds of billions of stars, most of them with planets, some of those planets in habitable zones, all of them separated from each other by distances so vast that our fastest spacecraft would take tens of thousands of years to cross them. Find the tiny smudge of Andromeda near Cassiopeia and remember, the photons hitting your eyes right now left that galaxy 2.537 million years ago, before our species existed. And remember that all of it is built from steps of 9,461 billion kilometers. 1 light year at a time. Now you know what that means. Now it haunts you. Good.